I'm going to work through an example using free body diagrams using second law of motion to address a few questions. So we have a system of three boxes, A, B, and C. A and B are connected by string, B and C are connected by a string, and the string is redirected over a frictionless pulley, and we are to ignore friction between A and its table, and A in the air, and B and C in the air. We're given the masses of the three boxes, so we're kind of hefty. 40 kilograms is a dense box. We want to find the force of tension in this string connecting box C to box B. And then we also want to know how far does box A move in a quarter second. And we'll get to that by using kinematics. Let's start with some free body diagrams. And, put my coordinates down. So I'm going to use coordinates where X goes to the right and Y goes up the page. Not really any reason to pick different coordinates than that. And let's do free body diagrams for the boxes individually. And I also want to do a free body diagram where I stick all three together into the same system. So free body diagram, and pick box C because that's the simplest case. I just have two forces acting on it. So let me label this free body diagram for C. C has a weight. When I look at that, this should be the shortest of them. Keep everything on the same scale. So there is the force of gravity, or the weight of box C. And what we're actually going to try to solve for is there is some force of tension. I'll call that tension for box C. Okay. Free body diagram for box B. So FBD for box B. Well, if there's a force of tension pulling up on box C, there's an equal and opposite force of tension pulling down on box B. So I'm going to put in that vector. So minus this tension, just meaning I flip the direction around. Box B has weight, and this is a pretty hefty one. So I put in the weight of box B, and then there is a string above it, and so there's some force of tension pulling up. Don't know what it is yet, but we'll figure it out. So I'm going to call that vector tension B. All right, and then free body diagram for box A. So free body diagram for box A. So there's box A. Oops, not vector. I don't know why I did that. Okay, box A has a weight. That acts straight down. That is entirely canceled out by a normal force from the table. but there is a force of tension pulling block or box A to the right. And I'm going to call that right now in the free body diagram tension A, but I know in magnitude tension A is just as big in an opposite direction as tension B, because I can ignore the weight of this string and the pulley is frictionless. Okay. All right, so if my system is C, there's the free body diagram. If my system is B, there's my free body diagram. If my system is A, there's my free body diagram. What I want to do now is I want to put all three of these objects together into the same system. And I want to do that because a lot of these forces are going to cancel out. Okay, so let me write out free body diagram for system of boxes A, B, and C. So there's the three of them together, and let's see what we can figure out. I know when I put B and C together in a system, these two forces, force of tension C up and force of tension C down, are going to cancel out. So I'm going to cross those out. Those cancel in the system, so they can't appear in this free body diagram. I know from equilibrium, the normal force is going to cancel out the weight of block A. So those two can't appear in the free body diagram for the system of the three boxes together. And then I have one other cancellation, and this one is a little bit more mind-bendy, but all this pulley is doing is changing the direction of the tension force. So I can get rid of, as an internal force, force of tension B pulling up on box B is going to cancel out with tension A pulling box A to the right. So I put these all together in the same system. Tension C cancels out minus tension C, that was pretty obvious. The normal force cancels out the weight of box A, and then tension B cancels out tension A. So those are internal forces that are equal and opposite in the system. And all that the pulley is doing is redirecting it. Now I have two forces that survived putting these three together in the system: the weight of box C and the weight of box B. So that tells me what the net force on the system is. And I draw out this free body diagram. This is going to be the weight of box B, and then I have the weight of box C, two forces. And I can use Newton's second law of motion to get at the acceleration. For my system of boxes A, B, and C together, this is mass of A plus mass of B plus mass of C times the acceleration. Okay, that is going to tell me the acceleration is going to be in the same direction as the net force, which is down. So acceleration is going to be net force is the mass of B plus the mass of C over mass of A, mass of B mass of c, the total inertia, times the acceleration due to gravity, and it is down, so it's minus, because I had picked up to be my positive direction. These forces point down, and the acceleration of the system has to point in the same direction, which is also down. Okay, so let's actually put in some numbers so we get a value for the acceleration. Mass B plus mass C is 50 kilograms, and the mass A, B, and C together is 80. So kilograms cancels kilograms. I'm just going to have 50 over 80, which is 5/8, minus 5/8 of G, which is 9.81 meters per second squared. So minus 6.13 meters per second squared. We'll need that acceleration to address how far box A moves and also tension. Because now that I have the acceleration, this is the same acceleration for box C, for box B, and for box A. They all accelerate together. I'm not going to have a situation where box C is accelerating faster than B or A and like pulling ahead. And I'm not going to have a situation where, like, say B lags behind and A is going to catch up to it. No, they are all going to accelerate together at this same 6.13 meters per second squared. B and C fall to the ground. A goes to the right. Okay, now let's address what is the tension between boxes B and C. And let's write out Newton's second law of motion for just box C, now that I have the acceleration. There is our acceleration vector. We know mass of box C times the acceleration. I have tension pointing up and the weight pointing down. So that's TC minus the weight of box C. I can rearrange this to get the tension. Move the weight to the other side. We'll have mass of box C, or box C rather, times acceleration plus acceleration due to gravity. We can just put in values now, because it is 10 kilograms. The acceleration minus 6.13 meters per second squared. The acceleration due to gravity is 9.81 meters per second squared. And so that is a tension 36.8 newtons. So tension between boxes B and C and magnitude 36.8 newtons. Okay, now get another little sheet of paper out. Move this guy up a little bit. We want to address how far does box A move in a quarter second. Well, they are all accelerating together. Our acceleration is constant, so the equations of kinematics are valid. We can use them. And so I'm going to pick the equation of kinematics that tells us the displacement in terms of initial velocity and acceleration. And it's also it is starting from rest. So we have a displacement A to the right. V0 delta t plus a half acceleration delta t squared, and box A starts at rest, so that's a 0. I can drop that term. I can take x initial and t initial equal to be 0. There's no reason why I can't start my ruler where box A is to begin with and start my clock at the start of this 0.25 second interval. So we're going to have, for that little simplification, final x is a half acceleration times the final time squared. And the box is being pulled to the right, so it accelerates to the right. That's my positive x direction. So this is going to be x final is a half, 6.13 meters per second squared times 0.250 seconds, quantity squared, and then that gives me 0.190 meters to 3 digits. So that's our answer for how far does box A move in a quarter second. Final position x final is 0.190 meters. So lots of things being practiced in this problem. Setting up free body diagrams, using systems. I picked box C to find the tension between these two boxes because box C has one fewer force acting on it than box B. Okay. I can solve it directly starting from the free body diagram for box C. For box B, I would still have to solve for this to make progress because box B is coupled together with box A. So the easiest way to proceed for the tension between these two boxes is to use the one on the end. We find that the acceleration is constant, so we can use the equation of kinematics, and that lets us solve for the desired distance.